seem to be quite as amenable to students asking questions. But I'm not going to try to get through everything here. In fact, I'd rather have you ask questions when you're not understanding things, because if you don't understand it, probably the rest of the students don't understand it either. So please interrupt me. No, one issue associated with this is I don't have your hearing, so I may ask you to use this microphone. But if you speak loud, I think I can probably understand your questions. Okay, so small angle scattering, like most scattering, you start with a source. It could be X-rays, neutrons, and I'm going to talk about light also here. Some of the experiments involve light. That's the source. Hit a sample, and then you collect the scattered rays, scattered photons as a function of angle. And you get a pattern that looks like this. Here's our famous X-ray diffraction experiments. We can explain where those lines occur using Bragg's law. And small angle scattering occurs down here, and very seldom do we ever see peaks associated where we can use Bragg's law. In fact, people who do X-ray diffraction don't even consider this data because there's no peaks in it. So what do you do with something that's as featureless as this? And this is the result that these are complex systems, typically where we apply small angle scattering, a lot of disorder, so we don't have nice lattices that give rise to a reciprocal lattice. And this generally occurs, this scattering occurs at very small angles, often below 1 degree, but certainly below 6 degrees. So this is where we're going to concentrate, down in this small theta region, very close to the main beam, within a few degrees of the main beam. Now, the book I like in this area, particularly for beginners, although it covers all to the advanced topics, does not use much quantum mechanics. So if you haven't had a quantum mechanics course, everything I've heard in the last 2 days is in this book, derived generally in a more simplified way. So I recommend you start with this book. It says polymer science here, but it's not at all restricted to polymer science. It's just a good first book to learn small angle scattering. And this is what I use. Diffraction is also covered there, but in a very cursory way. Okay, so let's start with Bragg's law. I'm not going to derive it, but I'm going to remind you some of the results of Bragg's law, and they're right here. Ordered structures give rise to peaks in reciprocal space, right? Reciprocal space is probed by moving the detector around the sample. That's how you find different spots in reciprocal space. And real space is the sample itself. That's where you move around the space we live in, this space. Okay, so that's one point. Large structures scatter at small angles. If this is the diffraction pattern of aluminum, these peaks are very closely spaced, scattering from closely spaced planes. And this would be the widest space plane. So when we go to small angles, we study large-scale structures. That's the concept of reciprocal space. Things that are small in real space are big in reciprocal space. So we, corresponding to going to small angles, we see large-scale structures. And the relevant size scale is roughly determined by Bragg's law. This is the distance between the planes here, and this is Bragg's law. I'm going to write that in this form, where Q is equal to 4 pi over lambda sine theta. One reason for this is because if you use different types of radiation, like X-rays, neutrons, and light, and you want to put them on the same scale, you can't use theta. You have to use the wave vector Q in order to provide on this axis here, on the x-axis. Another point is that Q is a vector. It has a direction. And you can't always determine the real space structure from the scattering data because of the blank problem. What problem? Phase problem, exactly. Okay, so nanomaterials, we're going to be exploring the nano world, are typically disordered structures. They're seldom ordered. Now, there are cases where people do ordered structures, layered structures and things like that, and get very nice peaks in small angle scattering. I've done some of those looking at the correlation of the porosity and anodized aluminum. You see very nice peaks in small angle scattering, but it's certainly the exception. Much more commonly, we do not see peaks, we just see broad profiles. Okay, so here's a disordered structure. This is one that gets studied many ways. This is the one that I cut my teeth on many years ago. And that is the structure of precipitated silica. Precipitated silica is everywhere. It's in food, anything that's processed. To give it a little more viscosity, you put this colloidal silica in there. It's in tires. Anything in the process industry, there's probably silica in there. And this is how it's made. You take this stuff here, which is soluble silicate, you acidify it, and you precipitate SiO2. Now it's glass, SiO2. However, when it precipitates in a very complex hierarchical structure. Hierarchical means it has structure on small scales. You can see these little particulate structures in here that probably occurs by nucleation and growth. And then someplace in the precipitation process, those things aggregate into these higher level structures, and we give those the name aggregates. You can see they're very well bonded together here. Those little particles are pretty much blurred out. There's a strong chemical bonding between those primary particles. And actually, these things then can organize into much higher level structures. So we've got things that range from a few nanometers down here up to tens of microns and even hundreds of microns, these very large structures that occur, say, during the drying process. Though this is something that's of a very large technological importance, particularly in the tire industry, because depending on how you carry out this process and what kind of structures occur at these various levels, you get different performance of a tire. Say it's wet traction, its wear properties, its heat generation. All this is controlled by the morphology of that filler particle. Now, you probably would wonder why tires are black. That's because they've got carbon black in it. But actually, modern tires have more silica in it than they have carbon black. They're actually a mixture of two. And carbon black has the same basic type of structure. Silica has a little bit improved properties over carbon black, so you could actually make your tires white now. Silica is more expensive, so that's why it's generally a mixture of carbon black and silica. So that's an example of a problem that has a very complex, disordered, non-ordered structure that we want to understand what its morphology is. And what I want to try to get across to you today is some of the tools that you use in order to characterize these very complex structures. So here is a scattering pattern. This is intensity versus wave vector Q. Remember, Q is 4 pi over lambda sine theta. In a Bragg sense, it's 2 pi over a Bragg spacing. Well, there's no peaks here, except actually there is a little peak down here. This is in the X-ray diffraction regime, XRD, and you do see a peak associated with the distances between the silica and oxygen atoms. So it's not a very ordered structure because it's amorphous silica, but there is, you can see atomic correlations out here in this region. So that was measured by powder X-ray diffraction. Here's a region here where it's measured by small angle scattering, generally covers this region of scale here. And remember, this dimension here is roughly 1 over length, or maybe 2 pi over length, or pi over length. At any rate, this would correspond to roughly 10 angstroms. This would be 100 angstroms, 1,000, etc. So we're covering, maybe 8 orders of magnitude in length scale, which is what you have to do if you're going to deal with these very complex structures. So this involves light scattering, ultra small angle X-ray scattering, small angle X-ray scattering, and X-ray diffraction. So there's 4 instruments here that are pieced together in order to give this curve. So let's sort out this curve now in terms of the hierarchical structure I just mentioned. So we explained this part that has to do with the structure on a very small length scale. Let's jump to this one. Here we have light scattering. Light scattering has a long wavelength, right? So we study even larger structures at small angles. And in this case, we can actually study structures of the order of 100 microns in size. So we're going from atomic length scales up to hundreds of microns, almost what you can see with your eye. So here's the structure you observe, and it turns out, and we're going to show you how to do this, but you analyze this data and you can get the size scale of this agglomerate. This is the largest scale structure in there. However, if you come down here, then you see a little break over from here to here, and the place where that break occurs is roughly 1 over that number, or 1,000 angstroms, and that's the lower level hierarchical structure inside. Inside the agglomerate is the aggregate. That's the one that's hard welded together, and that occurs there. And then you see another little break here, and that's where you get the size of the primary particles. So these are the 4 length scales that are depicted by this break, this break, this break, and then these little peaks out here. So that's a lot of information from what anybody knew before these experiments were done. People didn't have these. All they could really measure was the size scale of the primary particle. But all these other length scales emerge very nicely. They're just spelled right out. They're opened right up in reciprocal space where you can't get at them in real space, or it's very difficult to get at them in real space doing imaging, microscopy, or something like that. There's more to it than that, however, because the shapes of these curves, and by that I mean in this case, we're going to interpret these in terms of these power law regions. This is log of intensity, log of Q. So a straight line on that plot means it's a power law. It goes as Q to some power. So in this case, it's Q to the power minus 3.1. In this case, it's Q to the power minus 2. In this case, it's Q to the power minus 4. Have you heard minus 4 before? What's minus 4 correspond to? Anybody know? Somebody's law? Porod's law. And Porod's law occurs when you've got a smooth surface. Okay, so already you can interpret this. It means that this primary particle has a smooth surface. Probably can't interpret these others too, but we may get to that, maybe not. But this slope of 2 indicates this kind of very open structure, aggregated structure, and the slope of minus 3.1 means it has a rough structure. So we get a lot of information, not even with doing any analysis, just with a ruler. Well, there is some analysis here, but a very simple analysis, let's say that. Almost visual inspection from small angle scattering data, you can get the structure that you had no idea about for hundreds of years, what it was, you know. But bang, there it is. It just unfolds in front of you as you spread it out in Q space. Questions? Okay, so that's a reason why you would do the experiments in real space rather than doing imaging. You do them in reciprocal space rather than doing imaging in real space. Here's another reason. I used to work at Sandia Labs. Jim Albert is a scientist there. I think he's still there, could be retired, I guess. And he was doing the formation of foams, trying to make microscopic porosity in foams using TIPS, thermally induced phase separation. And he came up with this idea that you get these different types of structures. These are SEM images here, depending on the conditions of temperature and concentration that you use. And what you do is quench a solution that's a polymer solution there where the polymers are dissolved, and quench it below its theta point where it will precipitate, and you get these different structures. So he had actually developed ideas that this one was in a region where you would get nucleation and growth. This is in a region where you would get spinodal decomposition, and he started constructing this sort of qualitative model as to why you get these different structures. So he asked me to do small angle scattering on it, and this is ultra small angle scattering on that same sample, and you'll notice that there's very little difference between these two curves. So the conclusion is that this is an artifact of having a surface. This one looks like it might even be a broken surface. This looks like a free surface. But what you see in these images is hiding the fact that it's basically the same physical process that underlies this formation. the small angle scattering curves look almost identically the same. There may be a little difference in length scale up here, but basically the shape of the curve is the same. So we conclude that you've got to be careful about drawing conclusions from images, because you're just seeing the surface, especially when you're doing SEM as opposed to TEM. You're not seeing the internal structure, and you can't spread out these length scales like you do in reciprocal space. So this is the point. Images miss the similarity in this case. Okay, so now we're going to do a little bit of mathematics, but you've seen this done in more complex ways already in this course, but let's just take a little different angle on this issue of how you add up the phases, because we no longer have planes and planes of atoms or layer structures. We have a disordered structure. So how do we handle it? How do we do Bragg's law if there's no order in the system? So let's start with just the scattering of a wave from one electron, wave scattered from one electron. So this is the amplitude of the incoming wave, the size of these fluctuations. Then the amplitude of the outgoing wave, this wave here, is going to be that initial amplitude times 1 over r, right? It's a spherically progressing wave, so its amplitude goes down as 1 over r, okay? And we're going to represent the wave using complex notation, not sines and cosines. Okay, now, so let's look at this, what this constant is here. First tell me, this is the amplitude, this is an amplitude, so what are the units of the constant if r is length? Length, right? What do you think that length is? So that's scattering length, right? So that's why we represent the fraction of the beam scattered by this wave has the units of length. Very strange if you don't sort of look at it in this way. It has to do with the spherical wave, which we measure by the angle subtended by a detector, not the area of a flat detector, right? So that's why this is a length, and it is indeed the scattering length. So if it's an electron, I'm going to do this for electrons because we can talk about electron density, but we can't talk about this measuring neutron density, right? Neutron density is, to understand the fraction of beam scattered by neutrons, it's just the scattering length of the neutron times the number of neutrons per X-rays per square centimeter, right? Electron density. But that's not true for neutrons, right? To understand the scattering power of a neutron, that's beyond the comprehension of ordinary mortals. It has to do with detailed nuclear physics, right? But we have a number that represents it, the scattering length of a neutron. The scattering length of an electron is just the size of the electron, the classical size of the electron. So I'm going to use the terminology of electrons, realizing that it's all translatable to neutrons by just substituting the neutron scattering length for the X-ray scattering length. Okay, so here now I'm going to do many electrons, or many atoms maybe, something like that. Anyway, here's the amplitude. It's the same formula, except now I have to sum over all the electrons like this, right? So this is all done in Rowe's book in much more detail. I go from a sum to an integral, and I get this expression. Now, the scattering length of one electron, the electron density, and this is called the Fourier transform of this quantity right here. So I'm going to put those two together, the scattering length times the number density, and that's going to be this quantity, which is what? Scattering length density, right? Okay, so we're no longer talking about neutron density or X-ray density. It's just the scattering length density, and it covers both neutrons and X-rays. Okay, so that's the scattering length density. So in words, I always ask my students to say this so they don't forget it. The amplitude is the Fourier transform of the scattering length density. We're going to have some other words like that also, but remember that. The amplitude of the scattered wave is the Fourier transform of the scattering length density. I say almost, The almost has to do with the fact this is V mod infinity. I'm not going to cover that. It's in Rowe's book. Okay, so here's the electron density distribution, the scattering length density distribution, what the difference is. So now tell me what I said. The amplitude of the scattering wave is the? Exactly. Okay, so let's talk about that a little bit more. So here it is again. I'm going to pull the other amplitude out here. So this is the fraction of the scattering wave is the Fourier transform of the scattering length density. The problem is you can't measure it, right? Detectors don't measure the amplitude of a wave. All detectors measure the square of the amplitude of the wave, right? So that's written right down here. The scattered intensity is the square of the amplitude of the wave, and that is the square of the Fourier transform of the scattering length density, right? So that little square causes a lot of problems here. It does, you've been told it's caused a lot of problems. I'm going to tell you that that square is what makes the world reasonable to us, and I'll explain why that is. So here, this is crude, but what you see in an image is roughly the scattering length density if you're doing electron imaging, right? The bright spots, there's more electrons. The dark spots, there's less electrons. Well, that's pretty simplified, but generally it's a map like this. And the problem with that is that if you want to know the structure of a material, the structure is different here than it is here and over there. So if you're going to use an image to describe structure, you have to take the structure of the whole image. It's like asking, what's the structure of the United States? Well, you have to have a map of the entire United States because it's different at every little square foot anywhere on the planet, right? It's all different. So it's too much information, right? You can't do anything with the scattering length density because it's too complex. You can't get anything out of it. Okay, I'll come back to that point. So what we measure is the square of the Fourier transform of the scattering length density. Now this is a little trick here to get rid of that square. It's done in Rowe's book, and you can rewrite this just using mathematics as the Fourier transform of this function right here, and this is called the correlation function of the scattering length density. So what we actually measure is this. So tell me what it is. The scattered intensity is the Fourier transform of the, no, the correlation function of the scattering length density. Okay, there's a big difference between those two. Now, notice that this is an integral over u, so it's integrating over the origin. It's only measuring the differences, the correlation of different spots. Now that drastically reduces the amount of information, but it actually, that's what spreads things out in reciprocal space so we can actually see them. So this can't be inverted. This one can be inverted. We can get this function here. We can get the correlation function of scattering data by invert the Fourier transform of this expression right here. It doesn't tell you where every point is all over the United States, but it tells you the correlations. You can tell when you have a mountain here, you're likely to have a mountain 30 miles away. You know, it gives you those correlations of distances or the sizes of cities or things like that. It can give you differences, things that are associated with distances between things, not the absolute position in the universe. Okay, so let's look a little bit more at what we're doing here. So here, this is not the same function, but this is, I told you I did some work on anodized aluminum, and this is the SEM image of the surface of anodized aluminum. And you can see there's some little pores here. That's actually what they are. They're pores. They look kind of random looking. So this is the electron density distribution, N of R, right? Or scattering length density distribution. We use them similarly here. So if we take that, we can throw out the phase information by taking that image and constructing this function. This function is the correlation function of the electron density, right? And now I've got something that, rather than something that changes all over the sample, it's the same everywhere. If the sample is similar, is the same, you know, exactly where this particular pore occurs in the universe doesn't matter. The only thing that matters is how close this pore is to that pore, and that one is to that one. It's only the correlations in those distances which are left once you form the correlation function from the number density, right? So we get differences in distances. So if we do that, we get a function that looks like this. Now, if your supervisor asks you what the structure is, well, you can say, well, the correlation length between the pores is this distance right here, and the size of the pores is this distance here, and maybe there's some information about the shape of this curve, about what the pores are like. But now you've got a mathematical function you can analyze using models. But to analyze the entire sample using a model, you can't do. So this is actually beneficial to throw out that phase information and get a function that you can actually analyze. So the real space picture depends on the latitude and longitude. It's too much information to be useful. In this case, it depends on the separation distance. That's what this R is. This R here, not this R here. This is where you are in the universe. This is the differences. And it retains the statistically significant information. You don't have the details of an exact spot in the sample, but you have all the statistically significant information. So here's some more problems with real space analysis. Resolution problems at small q. You know, you have to go to TEM to get high resolution. That's very tricky. Seldom ever works for materials that I work with. There's opacity at large q. You can't get light through the samples when you have to study large-scale structures. It's a two-dimensional projection. And the big one, operator prejudice. I'm going to talk a little bit more about that in a moment. Okay, so let's talk about imaging versus scattering. Here's our same picture. Here's the correlation function. If I have this correlation function, I can Fourier transform that. So this is the correlation function of the electron density. This is the Fourier transform of the correlation function of scattering length density. And I get some other shape like this. This is what you measure in real space. If you do it right, that's very hard to do because you've got to do a three-dimensional correlation of all the structures, but I know of at least one paper where people do this. If you're a material scientist, you almost never do this unless you work for an expert in electron imaging. And experts know what they're talking about. They know everything I'm telling you. But your average, Joe Blow material scientist doesn't know any of this, and therefore makes a lot of mistakes interpreting electron microscopy data. Okay, so you can relate these two if you talk about the correlation function. They are Fourier transform pairs. And this is the one paper I know of where people have actually done this, where they've taken data on what carbon nanotubes are, Fourier transformed it, and they came to the conclusion that we'd come 2 years before, that carbon nanotubes are not nice little nanotubes like this, but they're very disordered structures. They came to exactly the same conclusion by properly analyzing the electron scattering, the electron imaging data. There were dozens and dozens of papers, maybe hundreds of papers, claiming that these are nice, short, little rod-like objects. And how can that be? How can you have these pictures that show little, perfect little rod-like objects when the scattering data and properly analyzed imaging data show that they're disordered? And the answer is operator prejudice. Choosing the data. Most graduate schools now teach ethics courses, scientific misconduct, and you're taught that scientific misconduct is plagiarism and fudging the data, right? Certainly is. That's not how people cheat today. People cheat by selecting the data. We call that cherry picking, right? You pick the data that you like rather than taking it all, and then you impose the model of your supervisor onto the data and you come to a conclusion. This is a very serious problem in material science and in health and biomedical sciences, choosing the data. So it doesn't fall in the category they tell you is scientific misconduct, namely fabricating data, plagiarizing data. It's selecting data, but it is equally scientific misconduct. And in my opinion, it's very prevalent. There's been several articles in the Wall Street Journal about the medical and biomedical research that they claim is only about half the experiments are repeatable. So students are getting the results their professors want. So I always ask this question. If you get an image like this and your professor, you show it to your boss and he says, well, you know, everybody thinks that these pores are highly correlated. Can you go back and look at the sample and see if you can find where there's nice ordered porosity in these samples? What should you do? Say again? Get better data. So you keep taking data until you get the one he wants? That's what most of you would do, I'll bet. Who's talking? Yes?
You'd use techniques that probes the same information but in a different way.
Good idea. Here's my answer. Get a new supervisor. Okay, so I'm not going to teach you all the different kinds of systems and the models people use. It's way too complex. All we want to do is get the basics, and my guess is, have you done any small angle experiments yet? So you probably will, and probably what you're going to study is particles and measure things like the Guinier Radius. So we're just going to cover the basics of simple systems. The simplest system is a particle, and almost every beginner starts by studying scattering from particles, and so particle scattering has been published over and over and over and over and over. So what I'm going to do is use our formula. Amplitude is the Fourier transform of the scattering length density. Here I have a particle. Its size is 2r. Its radius is r. It has a scattering length density, call it rho naught. It's in a vacuum. So what I'm going to do is calculate the amplitude and then square it to get the intensity, right? You all follow that, right? You know that the intensity is the square of the Fourier transform of the scattering length density. So we're not going to calculate the correlation function. We're going to go directly, calculate the Fourier transform of the scattering length density, and then we're going to square it down here. And there it is. Only one trick here: to get from here to here, you have to use integration by parts. And once you know that, you can work this formula out on your own. So here is the function for a single particle. Actually, I put an n in here to make it n particles. And that function is this red line right here. It has these very, very deep minima in it, having to do with the interference of waves as it goes through the different pathway through the sphere like this. Okay, we can also write this. If there's a solvent present, it's not in a vacuum. I have to put this as rho minus rho naught, where rho naught is this particle scattering length density, and rho is the solvent density. But that's the only change it makes. If I have more than one particle, I put an n in here. This is the volume of the particle. And this function here is called the form factor. It tells you the shape of the particle, and that's this part right here. And sometimes people put a square in here, sometimes they don't. So that's the formula for scattering from a sphere. Now, it's extremely difficult to get spheres that are this monodispersed, this all exactly the same size. Some people come reasonably close, but if you just make some Stuber silica or some particles, you're not going to see any valleys at all, because there's a size distribution there, and you're going to look at TEM and say, no, they're all the same size. Well, not true. They're not all the same size. There's some, maybe some little aggregates of 2 or 3, and they're all not physically the same size. So here's a distribution here. This is actually a fairly narrow distribution in this game. And there you can see that it wipes out those deep depressions. So, ordinary mortals can probably make particles with a size distribution like this. So you might be able to see 1 or 2 little bumps in here. But usually you don't see any bumps. Okay, so here's an example. This is a polyurethane with silica particles in there. And those silica particles are those white spots that are about the size of this bullet, this point here, those little tiny white spots that you see in there. And this is the scattering curve. And you see that there's no peaks at all, no peaks or valleys, right? It's just a monotonically decaying curve. Okay, so let's start analyzing it. First, you notice this is very close to 4. It is 4 up here. It maybe deviates a little here. So that tells you that these particles have what kind of a surface? Smooth, not spherical. They don't have to be spherical, but they have to be smooth. Okay, and maybe at shorter length scales corresponding to larger Q, there may be some roughness coming in here that gives rise to this deviation. Looks like we won't get to be able to talk about that much. But we are going to talk about what happens up here. This is called Guinier scattering. Guinier is the pioneer of small angle scattering. I actually met him once. He's dead now, from France. He did a lot in diffraction too. In fact, 2 primary books, which everybody has if you work in small angle scattering and diffraction, are his 2 original books. They're still great sources to understand things that aren't found in modern books. Okay, so what we're going to do is analyze this here. What do we get out of that? Well, if you take the function here and you expand this function and you square it, you get this formula right here. This is the contrast. That's the rho minus rho naught. There's the volume squared. And here's the form factor. That is the first few terms of expansion of the form factor. So it's just expanding that complex function I had before that gave rise to all of those that had sines and cosines in it. Expand it out, and you get this. So the curvature here, notice this goes as q squared. So that corresponds to the curvature in this region at low q, goes as this quantity right here, which is the intercept, times the initial curvature goes as q squared times rg. And this rg is called the Guinier radius, or it's also the moment of inertia or the radius of gyration. So it's not the hard radius. It's not the radius of the particle you would use in geometry. It's another function, but the relationship is for a sphere is that the Guinier radius or the radius of gyration is the square root of 3/5 times the hard radius is what we'd call the geometric radius of the particle. Okay, so basically from the Guinier region you get the size of the objects. What that size means depends on whether you have spheres or rods or more complex phase-separated structures, exactly the meaning of what it is, but it gives you the size scale of the structure. And you remember that I got 4 size scales out of one of those original sets of data that I showed you. So here's how you analyze it. My guess is you might do this in one of your experiments. You plot the intensity versus q squared and take the initial slope. You can also do this in another way. You can plot the log of the intensity versus q squared. And sometimes you get a better linear region here, a longer linear region. But you can see that you get very sharp deviations here. You can only do this as you approach q equals to 0. So even though this function here is far from that of a perfect sphere, you can still get the average, the mean size of those spheres from doing this Guinier analysis of the data. Okay, now what happens when you start to push these spheres together? And if you're studying the concentration dependence of colloidal particles in solution, you're going to start probably putting 10%, maybe 20%. Typically, you can even get up to 50% particles and still have a fluid. So what happens here is that you develop this peak in the scattering structure. So this is with this is low concentration here. And as you pack them together, you go from here to here. The curve, if you could do this at constant concentration at least, the curve would look like this. You'd go from this curve, and then this little hint of a peak would develop here. And then you get a very sharp peak as you pack them together as tight as you can. This is a very simple hard sphere theory, so it doesn't cover everything, but it gives you the basic idea. When you start packing things together, they're no longer random, right? You don't have a gas of particles. You have a correlated system where there's a very particular distance in here that's more prevalent than all other distances, which is roughly twice the size of the particle. It's the diameter of the particle as you pack them in very tight. So as you pack them in very tight, you get 2 pi over d here, where d is the size of the particles, and it has to do not with the size, but the distance between the centers there. It's measuring all those differences, right? That's what we talked about previously. Okay, so that's a simple idea what happens there. Here's some data. Wasn't expected, but we studied silica particles, and now these are not aggregated silica, but nice little individual silica particles in epoxy as a way of reinforcing the epoxy. So probably many of you study composites. People do small angle scattering. A lot of people start studying composite materials, making lots of mistakes too. And here's what you get. As you increase the concentration, you can, if you follow the area here, you see that these curves here are the highest concentration. You're getting something that's looking fairly close to the shape of this curve here. And that has to do with these correlations that develop as you pack them together. Now, when you look at this in more detail, what you find is that the packing distance is roughly 10 times the size of the particles. We know the size of the particles from a separate experiment under dilute conditions. And you can even get the size of the particles out of this in detailed analysis. This is something we still don't understand. Why these particles don't go, it's a hard sphere model, why they seem to have, they can't get close together. There's a distances which is much larger than the diameter of the particle that restricts them from coming together. Well, maybe the manufacturers put some fuzz on there or something. Well, this is an awful thick layer of fuzz. Maybe there's some repulsive interaction. Well, there isn't any repulsive interaction other than electrostatic at that range. So we haven't really figured out why these correlations are occurring at such a distance which is so much larger than the particle itself. So there's lots of things that still aren't understood in these situations. Okay, so this is the one that's relevant to tires. We're going to talk about using precipitated silica, that very complex structure that I showed you at the beginning, and what you want to do with that structure in order to make it an effective reinforcing agent for a rubber tire or actually any kind of composite material. So we actually, these experiments, we actually worked with the manufacturer who gave us samples of these structures at various stages in the processing. So I indicated that you take water glass, which is a fluid, dissolved silica in strong base, and you acidify it, and you bring down this precipitate. So this is the wet sample that comes right out of the reactor. Before it's dried, anything is done to it. And this is actually light scattering, because these are fairly large objects. And we can do a Guinier analysis in this region, and we get a radius of gyration of 3.5 microns, or overall size of about 7 microns. Now, we can't associate this with a, this is not a sphere, but you can still measure a Guinier radius, right? Or radius of gyration. So that's what we get when it's wet. Okay, then the next thing we do is that. Okay. Then we dry it, okay? So this is the dried stage. So we take this thing, which is fluid, still a fluid, just precipitate in a kind of a gel-like structure, and you dry it out. Then you take that dried structure and redisperse it sonically or just to stir it up in another solution, measure it again, and this is what you get. Okay, so you still have this same structure out here. Is this large length scale or is this large length scale? What is this, large or small length scale? Smaller length scale, okay. So this structure here, we're looking inside of the structure here, and we're looking inside of this bigger structure here. It's the same inside, but the size has grown, right? It's grown from 3.5 microns to 44 microns. In addition, notice that the slope here is 3.2. You remember what I said that was? Rough surface, okay? So you've gone from a rough surface to, on this structure, you still have roughness here, but you have this larger scale structure, which is much more open. That's the agglomerate structure. That's this whole structure here. That's determined by this slope here. That's how you tell that that is a very complex, stuck together structure, not at all spherical. Okay, then we come back and we take this and sonicate it. That is, put a sonication probe and try to bust up those agglomerates. And then we observe this one. And notice that it has decreased in size from 44 to 11 microns. So we're kind of reversing this process, but we don't get all the way back, right? We can't get all the way back to 3.5 microns. So we refer to this difference here, those ones that break up from the full size down, we call those soft agglomerates because they're easy to break up. However, you can sonicate the snot out of these and they don't break up. So we call those hard agglomerates. Okay, so why does this make a difference? It's because all the reinforcing is done by this length scale. These things don't reinforce. They're big floppy things that don't have any reinforcing ability. So what the tire industry tries to do is bust this up as far as possible. And I don't have time to go into that, but they go through all rolling mills and all kinds of processes, and maybe the manufacturers of these silica change it so they make a lot of soft agglomerates that will break up easily. But the whole idea of getting silica or carbon black into rubber is to break it up as much as possible, because all those big chunks do is form defects in the tire, and they don't do any good. All they do is cause trouble. Okay, so that's an application of this basic idea of, just from the Guinier radius, we came to all those conclusions. And we've already talked about this pretty much, but the other things that are left here to talk about are what are the meanings of these slopes. And I've given you an idea. You already know that this means a smooth surface structure, but what do these other slopes mean? We may be able to get through this actually. And there we need that. This is a really important topic in small angle scattering because it allows you to interpret data that does not have a slope of 4. Prior to this idea, nobody knew what to do with the X-ray data other than measure its Guinier radius. Nobody knew what to do with the slope other than 4. And it has to do with the internal structure. So this object here is a sphere. Its mass goes as r cubed. This is a disk. Its mass goes as r squared. This is a rod. Its mass goes as its length to the 1. And this object, it turns out, obeys the same relationship, except its mass goes as some strange power of the size of the object. Now notice this you would call 1-dimensional, 2-dimensional, 3-dimensional, 1-dimensional, 2-dimensional, 3-dimensional. This would also be a dimension. It's called the fractal dimension. It's what we use to characterize disordered structures. Everything from these aggregates to the surface of the earth, to the fluctuations in the stock market, used all over the place when you're dealing with disorder. It's a way of characterizing disordered systems, called the Mass-Fractal dimension. And then there's also a surface fractal dimension, which has to do with the roughness. So here's a smooth surface. The surface goes as the radius squared, right? 4 pi r squared for a sphere. Any smooth surface, you'll have that relationship. Maybe not be 4 pi, but something else. Now, if you have a rough surface, this doesn't work. That expression doesn't work, and we find that the surface area goes r to the d sub s. And you can think about this by taking a sheet of paper. Usually I bring one up, forgot about it this time. And the area goes as S squared, right? So one side squared, that's the area of a sheet of paper. Crunch it up, same area, right? Smaller size. No longer goes as the size of the object squared. It goes at some power that's more like 3 rather than 2. Okay, so that's an example of using this concept of dimensionality of a surface as well as the mass of the object as well. So this is a fractal surface or a self-affine surface. A fractal surface has overhangs like this. A self-affine surface is a stock market curve. Has no overhangs, but it still can be characterized by the same kinds of concepts of fractal dimension. Okay, so we're not going to go into the detail here, but here are the rules. I've already done this, well, I haven't done this. Here's the structures we just talked about. The Mass-Fractal dimension is here is 3. M goes as r to the r cubed. The Mass-Fractal dimension here is also 3, right? It's uniformly dense. It's not a sphere. It's porous, but it's uniformly dense. If you increase the size by a factor of 2, the mass goes up by a factor of 2 cubed. So it's still a 3-dimensional structure. This one, that is not true. The mass does not go as r cubed. It goes as some smaller power. Now, in addition, this one has a smooth surface. This one has a rough surface, so its fractal mass surface dimension is between 2 and 3. In this case, it really doesn't have a surface, so the mass and the surface dimension are the same. So that's pretty quick, but here's the result for how you interpret the data. When we're in the region where you're probing dimensional scales much smaller than the size, that is, you're at large Q, right? Large Q, small scales. So in that regime, you get a slope of 4 here. That's the Porod's law for a smooth surface. Here you get slopes between 3 and 4 for a rough surfaced object. And for a mass-fractal object like this, you get slopes between 1 and 3. So 1, if it was 1, what would it be? What structure does the mass go as the size? A rod, right. So this would cover a rod up to crumpled paper, which is about 3. But everything in between there, well, crumpled paper actually falls in this. It's right at the crossover between these two. So the mass fracture goes from 1 to 3. The best it can be is uniformly dense, and the lowest it can be is 1. If it was less than 1, it would mean it would be a disconnected object, which of course falls apart. Okay, so in reciprocal space, these rules typically for an aggregated structure come out like this. Here's the Guinier region. This is obviously schematic, not real data or anything like real data, but you have a slope here that goes as q to the minus Mass-Fractal dimension. That gives you the structure of this object. And then when you get down to the size of the primary particles here, it takes over to a slope of 4. So when you see this, you say immediately, I have a mass-fractal structure. It has smooth primary particles. Its mass-fractal dimension is this exponent here, which is typically about 2. And its overall size scale is determined by this point right here. So just looking at the data, you can learn a lot that you didn't know before you took the small angle scattering data. And here's a very complex structure. This is one of these tire silicas. So let's interpret it. Here's the curve. This is light scattering and small angle X-ray scattering, USACs and light scattering, ultra small angle X-ray scattering. So here's the overall size here, 116 microns. Here's a little break here. That is where you go from a hard agglomerate to a soft agglomerate. So that's a length scale of about this size right here, 116 to 7. Then when you get down to here, you're getting inside of that structure and seeing this structure right here. That's this break right here. And then you get down to the primary particles right here. So that's very much like the interpretation I just did. It says it has an extra break up here that tells you where the soft agglomerate and hard agglomerate crossover length scale occurs. Okay, then let's interpret the exponents. Here's a slope of -4. You tell me, what's it mean? Smooth. What is smooth? Primary particle is smooth. This is a slope of 1.6. What's it mean? Mass-fractal. And which structure is it here? Aggregate, the hard aggregate, right? It's this structure. It's the thing that reinforces tires. That's what you want. Okay? Then we have this structure here. What does that mean? The 3.2? Slope? Rough surface. Okay? And you can get the length scale here, but that's the length scale of this object right here. That's that much. That's the hard agglomerate. And then here's the soft agglomerate. I didn't put its slope here, but it's about the same as this, 1.6. So this one looks like a mass fractal, and this big structure also looks like it. Notice that it has the same shape as this, right? Statistically similar shape. So it has mass fractal structures on 2 length scales, and it has surface fractal structures on two other length scales, one of which is a smooth surface, okay? So we just did what people have been trying to figure out in the tire industry for the last 50 years by doing 2 experiments, a light scattering and a small angle scattering experiments. We sorted out what the structure is of a complex colloidal filler that comes from the factory. I don't know if we're okay, so this one has to do with the dispersion. This is the reinforcing part of the problem. This is dispersion. You say, well, why don't they just give the people these aggregates and not the agglomerates? Well, if they did, 1 tire's worth of silica would fill up the stage. It doesn't pack. You can't get it into a bag. Okay, so they have to make the agglomerated structures in order to get the stuff to pack. And then it's the responsibility of the tire manufacturers to break up all those aggregates using a bunch of different processes. If you actually break it up, this is putting it through the kind of milling that they put tires as they're milling this silica into the tires. And you'll see it goes from this structure. This is what we saw. This is the aggregate. This is the agglomerate, the aggregate, the primary particle. And it breaks up, and you lose this aggregated structure. So your soft agglomerates break down to hard agglomerates, and if you really beat the snot out of it, you can actually break it down to the size of the aggregates, and that's the size, that's the reinforcing agent. Now I left this as a problem, so what's the ideal size of an aggregate? Well, that's another issue. Got to think about what reinforcing means and what length scale you mean. And it has to do with the fact that if you make things too big, it comes floppy, right? And I've got a review paper called How Nano Are Nanocomposites, which if you're working in nanocomposites, you should read. Very simple title, How Nano Are Nanocomposites. You make things too big, they become floppy. If you make them too small, they don't reinforce. There's kind of a trade-off between those 2 length scales which determine what the size of the reinforcing agent should be. And the next section of this talk, which you're not going to get to, explores these various kinds of structures and how we figure out what they are. And the summary I just gave you, the answers come from small angle scattering. And this is the paper I was just talking about. If you're working in composites, I strongly suggest you look at it carefully, because it gets the relationship between the structure and the reinforcing ability. And material scientists generally don't do that. They just say one is better than the other, but they don't ask, well, what could it be? Or what's the best it could be? Because there's a lot of numbers reported in the literature which is better than they can be, based on very simple models. So we're not going to get to the rest of this, but if you see pictures in there that looks like something you're working on, come and talk to me. And right now, I guess we go to lunch, right?